Question 9, he discovered that the orbits of the planets are ellipses. Of course, that's Kepler's first law, so Kepler's best answer for number 10, A for number 10. Question number 11, the Occam's razor states that that's the keep it simple, silly argument, and that is B, that in explaining natural phenomenon, the simplest explanation is preferred. Question number 12, most of the mass in the Milky Way galaxy is located A, in the halo. Question number 13, if we look at a photograph of many galaxies, and assuming that they were formed at the same time, the galaxy that is furthest from us, C, will appear youngest, because it took longer for its little photons to get to us. Question 14, say you're standing on the equator, and you look out at Polaris, where is it going to be? Actually, it's going to be very low A on your northern horizon. Question 15, we experience nighttime because D, or when the side of the Earth that you're occupying is facing away from the sun. As the Earth rotates, we get nighttime and daytime and nighttime and daytime. Question 16, by locating the North Celestial Pole, you can determine your latitude C by looking at the altitude of Polaris, or the North Celestial Pole star. Question 17, why did Ptolemy have planets doing those little loop-de-loos? The best answer there is D. He did that to explain the retrograde motion. Question 18, has Polaris always been the North Star? Nope, because of precession. So best answer for 18 is A. Question 19, why is it summer? When it's summer in the northern hemisphere, it's winter in the southern hemisphere. That's because C, the northern hemisphere, is tilted toward the sun, and the sun's rays are most direct at that time of year. Question 20, on a cosmic calendar, if you put the Big Bang, day 1, and where we are as right before we've come full circle for a year, the dinosaurs became extinct, E, in late December. Question 21, the sun dagger in New Mexico basically pierces the center of that structure, D, at noon on the summer solstice. Question 22, Kepler's second law, which states that planets move around as orbit sweeps out equal areas and equal times, has the consequence of D, a planet will travel faster when it's at what we call perihelion, nearer the sun, and slower when it's farther from the sun. So D's the best answer there. Question 23, if you see Polaris directly over your head at midnight, you must be B, at the North Pole. Question 24, the distribution of mass in the Milky Way galaxy is determined by the stars orbiting the center, or the rotation of the galaxy. So those were each worth 1 point. So now for the short answer, these were each worth 2 points, and in some cases you kind of see, for instance, 27 and 29, I actually added a term. So listen up, especially for those. If you have those written down, then you get the credit for that. But in some cases, you got 1 out of 2 points. So I was after precession for 25, the process in which the Earth's axis of rotation is undergoing this coning motion. I was after galactic recycling for 26, the process by which stars live their lives, create heavier elements, and then give that back for new stars to be born, galactic recycling. I think if you put stellar recycling or star recycling, I think I gave you 1 out of 2. Question 27, I was really after zenith as the direction. It doesn't read right. The location direction above your head in the local sky is called. So if you put meridian, I also took that. So zenith or meridian. Question 28, planets appear to move backwards. We call that apparent retrograde motion. Question 29, the Earth orbits the sun on, in this case I was after the ecliptic plane, but if you put axis or tilted axis of rotation, I counted that one right too. So, question 30, it's altitude that is the angle an object makes in our local sky with the horizon. Question 31, astronomical unit is a unit to measure distance that is actually the average distance between the Earth and the sun. And the terminator is the line between the dark side of the moon and the side of the moon that we see that's lit up by the sun.
You have altitude on the 30?
Mm-hmm. Altitude for 30, yeah.
I don't want to cause you, that points what I have latitude.
Do you? Okay. Well, she's pointing out I missed one of hers. So, that whole latitude and altitude, is it just me or does that drive you nuts too? Just switch around those two letters, so, yeah. Thanks, though. I'll be more careful next time, Susan. It's fine.
Okay.
I'll be more careful next time. So these were each worth 3 points apiece. So kind of the format of this test is the way all the tests go. So the first question was basically, again, about a light year. Explain how a light year is a measurement of distance and not time. And so I saw some of you drew the same figure I did. But basically, a light year is putting an object so far away that it takes light 1 year to get to us. Question 35, I was a little picky with this. How do you find Polaris using other stars? And the answer is the asterism, the Big Dipper. And so I really needed you to say something about you use the bowl stars on the Big Dipper to find Polaris. If you use the handle on the Big Dipper to find Polaris, I took one off. Okay. Question 36, summarize Kepler's first law. Of course, it's the shape of the orbit of the planets are ellipses, and the sun is at the foci. Question 37, I wanted you to give me 3 of 6 ways in which we are never sitting still. So that's, of course, the Earth is spinning, the Earth is orbiting the sun.
Check marks wrong.
Check marks are good.
Oh, check marks are
Yes, check marks are good.
I was like, oh my God.
Yeah, I'm glad you asked. No, check marks are good. And then if you see something, so check marks are good. And if you see something that's just kind of like a line like that, it means that something's okay, but not quite right. And if you see an X like that, I couldn't really find anything right about it. So, I know, sad face. So 3 of those ways that we're always moving. The sun is orbiting the center of our galaxy, which is a supermassive black hole. And also the sun is kind of bobbing up and down within our local group of stars. Number 5 up there is that actually the Milky Way galaxy is moving relative to the other galaxies. And number 6, just simply because our universe is expanding, we are relocating on the fabric of space and time as that's going on. Question 38, why do we only see one side of the moon, the near side of the moon? And that's because of synchronous rotation. So the moon completes one orbit on its axis the same amount of time it completes, completes one rotation on its axis the same time it completes one rotation about the Earth. That's synchronous rotation. Then 39 was about Galileo. I only needed 2. So sometimes, like for question 39 for this test, I got kind of carried away and I thought you were supposed to give me 3. So if you gave me 2 and I counted it wrong, let me know, because really you only had to give me 2. Okay? So Galileo did many things. He did not invent the telescope, but he did many things to reinforce the fact that the sun is at the center of our solar system. Yay, Galileo. Okay? So those are for you to keep. And like I said, I'll be posting this answer key under doc sharing. Probably this weekend. So while I'm thinking of it, I was thinking about this topic, and it seems a little technical, you know, the whole light thing. But honestly, how else do we look at stars? You know, we look at stars because they are sending us light information. One of the things I'm going to try to convince you of, maybe it's not a hard thing to convince, but those stars are also sending us other information. Okay? I mean, it's not just the light we see. There's stuff hidden in the light that they're sending us. So, like, for instance, this actually is a fingerprint of the sun. Okay, the sun sends us white light, and you know you can take a prism and break the white light into a rainbow. So that's a rainbow. But can you see those little dark marks? Okay, we'll be talking about those. Those are called absorption lines. And those absorption lines, if you know what you're looking at, and you probably just have like a computer program to do it, you can match it up with elements.
With what?
Chemical elements on the sun. Okay, so it's like a finger. It's kind of like a DNA for stars. So We have to, and scientists have been very creative at just being here on Earth and understanding more and more and more about the cosmos. It's just amazing. So what we call light actually is one type of, I call it a cousin, of energies called electromagnetic radiation. So I brought a poster here. Okay. So sometimes they call all of these cousins you're going to see, sometimes they call them all light. But like for instance, gamma rays, there's the cousins. Gamma rays, X-rays, ultraviolet, infrared, microwaves, radio waves. You're going to see them on this poster. They're all electromagnetic radiation, okay, and sometimes, like I said, they're collectively called light. So as I have this, if I were to ask you of the cousins, which one are you least worried about getting hit with, you'd probably say radio waves. Bring on those radio waves. We're probably getting bombarded with radio waves right now, which is another type of electromagnetic radiation. You have very long waves, very unenergetic energies. Gamma rays, think of Hulk, right? Yeah. So you don't want to get hit with gamma rays, okay? So kind of as they're listed up there, okay, they're also on this poster that they're listed here. And we'll just kind of start kind of thinking about this. This is the most energetic, most E for energetic, okay, and down here, radio waves, this is the least energetic. But all of these energies, all these families of energies, okay, they have some similarities. They're collectively called electromagnetic radiation. So the similarities they have here, and just kind of think of them, like I said, as all being related. And you know gamma rays are most energetic and radio waves are the least energetic. But they are energies that all travel at the same speed. And they travel at c, the speed of light. And wasn't it just the last unit when we said you can convert matter into energy according to this, okay? E is equal to mc squared, where the variable c is the speed of light. Very fast. The speed of light is very fast. The thing about light, though, is if you have any sort of atoms or molecules, if you have air, if light is traveling through Earth's air, it travels more slowly than if it were traveling in outer space where there's no molecules, no nothing. Okay, so speed of light is usually what we call in a vacuum, nothing there. The other thing about all these families is that they travel in little packets of energy called photons. So where it says photons here, this is a little packet of energy. And you're going to see packet of E. You're going to see this little packet of energy on a figure coming up here in a minute. We say that they travel as particulates, photons, particulate energy, but they also have this wave function going on. So that's what we call the dual nature of light. Again, sometimes people say light, but they really mean electromagnetic radiation. They really mean all of it. Okay, so here we go. Can you kind of see the wave? We need to kind of get a fix on what waves look like. The description here says, and I didn't bring one, but if I were to go ahead and have a jump rope and fix the jump rope to the wall and go ahead and wiggle it, okay, that's kind of what they're doing there. Okay, you could see a crest and a trough, and a crest and a trough, and it would go through my jump rope. Okay. The thing that doesn't work, though, for the jump rope and light is that light has this going on, so it has wavelengths, okay, or it has waves, excuse me, but it also has little particulates, and that doesn't work for the jump rope because you don't see little particulates traveling, okay. So I said photon. I kind of think of, well, I guess there's not a photon on there. Okay. So when you see a wave like this, an important thing for energies, all these different energies are traveling in, have this sort of form, is how long that repeating unit is. It's called a wavelength. And actually, let me go ahead and kind of get the ball rolling here. Anytime you see the word wavelength, I want you to think of this, it's a Greek letter, it's called lambda. You make it like, well, you can make it however you want to. It kind of has like an upside down V, like a carrot with a lid. That's lambda. That means wavelength. Okay? That's a symbol. Like C is the symbol for the speed of light. Lambda, that thing right there is the symbol for a wavelength. The thing is, I said gamma rays, you know, gamma rays you don't want to be hit with, or you turn it off. Gamma rays are, the wavelength for gamma rays are teeny, 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 tiny. Okay? The wavelength for radio waves, oh my gosh, they could be like 2 miles. It takes about 2 miles to go from crest, okay, to crest for radio waves. Both traveling at the speed of light, though, and okay. So wavelength is important as to what energy it is. Okay, yep, there's my little lambda. Okay, so it's a little carrot thing. We're talking about wavelength because it's one of 2 ways that you can say which cousin you're talking about. Okay, which energy you're talking about. Wavelengths. Another important feature of electromagnetic radiation is frequency. So the way I think about frequency is basically somebody has a counter, okay, and they're standing still, and this wave is passing them. Okay, this wave is passing them, and he's standing still. So he has a counter to say in 1 second how many waves passing. Okay, so frequency, that's frequency. How many waves pass a certain point in 1 second? So it's cycles per second. Okay, that's what frequency is. And actually, if you've heard of hertz, HZ, a hertz means per second. I don't know why they didn't just say per second, okay? But a hertz means per second. So that's frequency. So, see, okay, here's one for you. Remember I said gamma rays are teeny, 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 tiny, okay? So here's the deal. Does this make sense? If I was the counter and little tiny, gamma rays were passing me, do you see where the frequency would be very high? Frequency would be very high. Okay, I'd have a lot of them passing in 1 second. Okay, so with a small wavelength for gamma rays, okay, they have a high frequency. Okay, I have lots of crests passing at the time. Change gears to the radio waves. Oh my gosh, you know, a couple miles, you can travel the speed of light. Okay, I don't know how many I'm going to get in a second, but it's going to be fewer than these. So with long wavelengths, like radio waves, they have long wavelengths and very short, small frequencies. I shouldn't say short, they have small frequencies. The number of cycles per second is pretty small. So on this poster, they have both of that information. Let's see. Notice there on the left, it says frequency in hertz. And there on the right, it says wavelength in centimeters. Okay? So if we just look at frequency, notice frequency, though, is basically we have to take that number, and it must be 10 raised to that number. So let's pick on, let's pick on these. It's got gamma rays. Notice it added another cousin, cosmic rays. Okay? There is some overlap. We see gamma rays here, X-rays here, kind of overlapping. But my point was going to be, if we pick like gamma rays up here, it says 21, that means 10 raised to the 21st power is the number of cycles per second. So 10 to the 21st, there you go. For gamma rays, this is what it looks like. This is what we got going on. For gamma rays, just looking at that poster, 10 to the 23rd power, that means, oops, I'm going to put a 1 and I'm going to put 23 zeros. Okay, that number of cycles in 1 second. Okay, that's my point. While we're doing that, let's look at the radio waves, just for kicks. So radio waves down here, let's see, radio waves. Let's go 10 to the 4th. So if we compare that to radio waves, it looks like this. Radio waves. 10 to the 4th per second, 10 to the 4th hertz. Looks like this, 1, 0, 0, 0 cycles per second. So anyway, that's a lot of cycles per second for the gamma rays. Okay, that's not very many cycles per second for the radio waves. All right. So for any of these cousins, if you were to take their number over here, their frequency, time their number over here, their wavelength for the same cousin, you would get the speed of light for each of them. They're constant. All right. So that might come in handy too. All right, so actually I really like this figure. That's one of the reasons that I bought this textbook, because it's good. So it's actually exactly what we've been talking about. Can you see from left to right? Okay, you see gamma rays, X-rays, ultraviolet, you see visible, infrared, radio, okay, and microwaves is in there too. So the next one says, and that kind of dims these lights, says, well, how big is that wavelength? Well, in some cases, it's pretty darn small. So for instance, starting with X-rays, it is about the diameter of a hydrogen atom. That's how big the wavelength of that energy is. Going up to the less energetic energies, okay, microwaves, about the size of a baseball. Okay, radio waves, one repeating unit can be about the size of a football field. Now I said like 2 miles, but longer wavelengths. And then frequency. So I like this because it emphasizes with the shorter wavelength for the more energetic energies. So we said more energy, more E. We have shorter wavelengths and we have higher frequencies. Teeny tiny, okay? For the less energetic ones over here, we have longer wavelengths and lower frequencies. All right. So here on Earth, these are things that actually emit these energies. Okay, so dangerous gamma rays can be emitted when atoms decay into other atoms radioactively. X-ray machines, light bulbs emit visible light, visible energy. One of the things that we count on is this infrared here. Actually, that is thermal energy. Thermal energy, infrared. And so that's why people ooze thermal energy. It's a type of electromagnetic radiation. Radars, microwave ovens, radio transmitters. But most importantly is this one. So down here at the bottom, finally, are what does all of this have to do with astronomy? So I said that actually stars are giving us more than just light. Stars are giving us other information. I will say it's not just stars that we need to study, okay, but other things. So these are neat things we'll be talking about more later, but starting with gamma ray bursts, very energetic events. We detect black holes' presence by the presence of X-rays. Okay, one way to study the sun, out of many ways, is in the ultraviolet. Heat is a signature of forming stars and planets. When we talk more about way back when, the Big Bang, BB for Big Bang, actually in this long wave energies of the microwaves, okay, that's where we are seeing kind of the hiss of the Big Bang. And then radio galaxies are just another sort of phenomenon that some galaxies do for us to understand what's going on there. Okay. So every cousin, if you take the wavelength times the frequency, you get the speed of light. So automatically, speed of light's a constant, automatically you can backtrack and knock out, if you know one, either wavelength or frequency, you can get the other one. But here we have an example of a wave. The wavelength is 1 centimeter, okay? And its frequency in hertz are 30 gigahertz. And a giga means 1 billion times. So that's 30 billion hertz. So what if then we go ahead and instead of going like this, we go twice as much, okay? We go twice as fast. If it's kind of a rope connected to the wall, we're going twice as fast. Well, that means that our frequency doubles. Okay, instead of 30 gigahertz, we have 60 gigahertz. But that means that our wavelength is half. Then let's go ahead and if we call this A, B, and C, scenario A, B, and C. What C does here then is basically shaking it, 4 times as fast as A. And if we do 4 times as fast as A, that means our frequency is 4 times 30 or 120 gigahertz. That means our wavelength is 1/4 of what it was before, which is 1/4 of a centimeter. So if you're a math person or kind of a physical science person, if we multiply these numbers by each other, we get the same number. Okay, it's remaining constant. Wavelength times frequency. That's a constant. It's the speed of light for electromagnetic radiation. So just to kind of emphasize, as those are written A, B, and C, we are going to a shorter wavelength and greater frequency. Okay, and then just to kind of remind you that for electromagnetic radiation, if you take the wavelength times the frequency for any energy, okay, you come up with the speed of light. All right. So, like this poster, I think does a good job emphasizing. There's a lot of cousins here. The whole radio waves, gamma rays, and the energy that we count on every day for us sighted people is right there between 15 and 14. Okay, 10 to the 15th and 10 to the 14th cycles per second. That's light. But there's all this other energy. I like to kind of think of it as just, it's stuff you don't see, but it's there, right? You don't see it unless you're looking for it in some cases, actually. So with regard to light, that little band of energies we count on so much, you need to kind of understand a little bit how light breaks out. And of course, you can take white light and break it down into components by running it through a prism. Newton found that out. And the colors of the rainbow are red, orange, yellow, green, blue, indigo. Who uses the word indigo except for like a crazy 2-year-old? I want indigo. And violet, okay? So a mnemonic device to remember, there's 7 colors, okay? I think this might have been on one of the New Cosmos episodes, came out last year, it's not that new, but that actually Newton did not like the number 6. 7 was a better Newton number for him, for colors. So that's why we got indigo. I'm like, okay, red, orange, yellow, green, blue, violet. I got it, right? Violet's purple. Okay, but he stuck indigo right there. So what that mnemonic device does for you is it helps you kind of put in perspective the colors with regard to wavelength. Okay, so what I'm trying to say here is red is the longest wavelength, longest lambda, longest wavelength, and violet is the shortest wavelength. And the cool thing about kind of all of these cousins and how light fits in is a little bit longer than red is IR. Of course, RR stands for infrared. So I like it. It brackets the visible colors. A little bit shorter than violet, okay, is ultraviolet, UV. The reason that we, an energy from the sun that we protect ourselves from. You know, is it visible to our perception? No. Is it there? Yes. So ultraviolet radiation. Okay, so it's the colors, the light, visible light is bracketed by infrared and ultraviolet. That's handy dandy. Okay. So I promise not to like belabor it too much, but we do need to talk a little bit about chemistry. Chemistry. That's my other job. So I teach chemistry. My degree is in chemistry. But we do need to talk a little bit about chemistry, just a little bit. And stuff that you're probably already familiar with, like stuff is made up of atoms, okay? But what astronomers have done is very clever. They understand the nature of an atom, like here on Earth, okay? And then what they know about an atom, how it behaves and stuff, how it gives you information, okay? They can apply that then to information that's coming from celestial objects. The sun, remember a little bit ago, we saw the sun, those dark lines, okay? For instance, that all has to do with atomic structure. It all has to do with, they understood that electrons make these little transitions I'm going to talk about, okay? It does it here on Earth, it does it up there in outer space, okay? So it's important. Atoms are your friend. Okay, so we need to talk about, and I know this is kind of like astronomy is sometimes called astrophysics, so it's kind of a branch of physics, astronomy is, when my degree is not in physics. But physicists talk about a lot smaller particles than these, okay? If you've heard of the particle accelerator, we'll talk about that later, but they like to break atoms into tiny little pieces. But the three main pieces we need to talk about, and chemists usually talk about, are this, okay? We have, and they're kind of shown, I like this figure. I think this is a figure from your textbook, all right? So basically, that little thing in the center there, that thing, that little hard thing, is called a nucleus. I don't know if you can see that, the word nucleus down here. That thing is called a nucleus, that little hard center. And so what they did was to try to blow up the nucleus, not really blow up the nucleus, but make the nucleus bigger. This thing right here is an enlargement of that little thing in the center. Okay? So all atoms have a nucleus, okay? And the nucleus, if we were going to look closer at it, looks like this. So you kind of see the two colors, the gray and the red, okay? And those two things in the nucleus are protons and neutrons. Nucleus, okay, are protons and neutrons. Protons, they're positively charged, okay? The important thing about protons in the nucleus is they say what sort of element it is. So, for instance, hydrogen is an element, iron is an element, calcium is an element, okay? Basically, your kind of potassium is an element. So in all those different elements I mentioned, they have a set number of protons in their nuclei. And that's what tells what sort of element it is, okay? Isn't that cool? I love it. So also sprinkled in the nucleus are these neutrons. Neutrons are like Switzerland. They are neutral. They don't have any charge, okay? But they do have a significant mass. So the two things that gives an atom mass, the two things that give matter mass, right, okay, are protons and neutrons in the center. All right, that thing that kind of makes me itch, this stuff right here, okay, those are actually electrons. Okay, it's what we call the electron cloud. So the fingerprint thing that our sun gave us information, okay, actually it's what the electrons are doing. We're going to focus a little bit more on what electrons do here in a minute. Okay, but this little cloud right here, these are electrons. And it says, I can see this caption here, electrons smeared out in a cloud around the nucleus.
Do they orbit around the nucleus, or is that
They used to think, he asked if the electrons like orbit, and they used to think that, but now it's actually, it's more of an electrical attraction, and they don't really orbit, they are in a cloud, and that's kind of, but they aren't like, it's not a gravity thing. And you really don't, it's like Heisenberg's uncertainty principle, you really don't know where they are. You can't pinpoint them down and know what energy they have, both. So, yeah, they don't really orbit it, but they're, and they make shapes and have play dates, and, well, they don't have play dates. So, still again about the atom, just a single atom. There are a couple characteristics of an atom that you kind of need to know when we're talking about atoms. One is the atomic number. And all that means is if you looked in the nucleus and you have counted the number of protons, you've literally counted the number of protons, and that's the atomic number. Okay, and I already said that the number of protons say the identity of the element, so that means the atomic number gives you the identity of the element. Okay, number of protons. The other thing, in order to have, or there's a few more things, two more things. Another thing is we said that electrons are in a cloud outside the nucleus. Okay, electrons are doing this outside the nucleus. Now, here's the deal. For most normal atoms, the number of electrons out here, because electrons are negatively charged, okay, the number of electrons are the same as the counted number of protons in the nucleus, most atoms. That's neutral. Okay, that's neutral. So, for instance, helium's pretty simple. Like if we pick on helium, okay, a helium nucleus, this is the helium nucleus. I would have to go, it's atomic number 2, so I have to put 2 protons in the center of the nucleus. And I'm going to go ahead and snap in 2 neutrons just for kicks. Okay? And I'm going to say that just because I have 2 protons, so atomic number is equal to 2, I'm going to call this helium, and it is. And then, just to kind of finish this thing about electrons, most helium atoms, normal here on Earth anyway, let's see, I'll pick purple. They have, there's a negative there and there's a negative here. Okay? They have 2 electrons. Okay? So the number of protons they have is equal to the number of electrons they have. That's neutral. The one last thing we talk about with regard to atoms is this. Okay? Now, I know it says atomic mass number, but I usually learned it just simply mass number. You know, I don't usually use the word atomic, but I guess you can. So the mass number, or atomic mass number, means that you, again, have dived into that same atom of interest, and you have counted protons and neutrons, and you've added them together. Okay, that's the atomic mass number. So, for instance then, let's go back up to the helium. Oops, it went away, didn't it? So, helium, we said, has 2 protons, and I gave it 2 neutrons, and that was the nucleus, and I gave it 2 electrons. There's my helium again. What's the mass number for that? It is 4. Very good. And how'd you get 4?
2 plus 2.
Yep. 2 plus 2. Very good. Perfect. Let's do one more slide. I'm trying to decide where to. No, let's go ahead and take a break, and we'll come back with isotopes. Okay? All right.